Hello again. So in today's workshop, we're going to be discussing something that I call permission-based chiropractic. And as an extension to that, we're going to be talking about this thing called adaptability testing and how to identify the dominant neurological level. So if you've watched previous workshops, you've probably heard some of these terms referred to previously. And if you haven't, then it may be a good idea to go back and watch some of those other workshops as well. But we'll be explaining this in more detail today. So all of these workshops can be accessed at the website, so www.superhealthy.com.au, and there's two places you can go to find all this material. The first place you can look is in the blog, and what you can find there is some of these videos are posted just in the order that they're produced, or you can go to the program section and there's actually a structured continuing professional development program that you can register for there, and there are additional technical, clinical, practical workshops in there as well. So permission-based healthcare, I guess if you think about the term permission healthcare, you're probably thinking about informed consent, which is like a conscious and a cognitive process between a practitioner and a patient, where the practitioner informs the patient of all the risks and benefits of their proposed management, and then the patient makes a conscious, informed consent. They inform the practitioner that they're willing to go ahead with that treatment. So we're not talking about that here. We're talking about a different type of permission. So in this context, we're talking about the need to know which therapeutic vectors will be most welcomed by the human physiology. So we're not talking consciously and cognitively. We're talking subconsciously to the physiology and asking for responses, for feedback from the person's physiology. And we're going to be talking about an examination method to ask the body which intervention produces the observable improvement in signs of adaptability, so improvement in physiology. So in a sense, we're talking to the body more than we're talking to the person. So we're talking about a process of examination to differentially diagnose where and how best to deliver a therapeutic intervention. In the context of today, we'll be talking about percussion therapy and using the 3D energy gun. So we're asking for a tick or we're asking for a cross from the person's physiology as to whether something is acceptable or unacceptable to that physiology. So another term that's we've probably very used to is this idea of differential diagnosis. So I guess traditionally this is kind of a form of triage. So we're ranking, we're trying to determine what is the worst, what is the quickest, what is the most urgent priority, and then we're going to intervene on that particular thing that is the top priority. So here, we're looking at it from a slightly different point of view. We're proposing a different kind of differential diagnosis. So we're going to be using a neurobiofeedback approach. So another question that we can ask the human physiology: which therapeutic impulse do you like the most? So it's a subconscious, it's an unconscious thing. We're tapping into the neural pathways, we're putting in afferent information, and we're going to be observing efferent changes as a result of that afferent information we put into this person's neurology. Another term we're going to be talking about is this idea of a dominant neurological layer. So we've talked a lot in previous workshops about the neural gate system and how this has to prioritize afferent information. There's so much information traveling in through the sensory system all the time that the nervous system has to be able to make care priorities as to which it needs to listen to. So the ranking, the most important, will direct the most dominant efferent outputs. This is what we're calling neurobiofeedback. So we can find that afferent and efferent pathways can be impaired by some form of interference. So this is usually going to be in a kind of a yin and a yang response, leading to imbalances. So too much function, too little function can result. So again, if you've watched previous workshops, you'll hear the fact that I've said, I believe there's a very strong correlation between the chiropractic concept of subluxation and the physiological concept of neural gait dysfunction. So they seem to have a lot of similarities in manifestation. So here's what we're thinking about. At any given time, there may be a dominant neurological layer. There's something that's predominating in the nervous system. So this is expressed as the highest priority, abnormal, afferent, and efferent pattern. What you're feeling and what your body's doing is a result of this prioritization system. So this dominant neurological layer could be a location or it could be a pattern. So how do we locate this dominant neurological layer? So input into the dominant neurological layer with an impulse vector. So it could just be a gentle touch that reduces interference, results in visible signs of physiological improvement. So if you press somewhere and that makes the physiology feel better, then the physiology will improve. So in a sense, the body physiology likes that therapeutic impulse. If the therapeutic impulse is introduced which does not improve afferent and efferent transmissions, then you're not going to see an improvement in physiology as a result of that impulse. Similarly, if you're not touching the right layer, the right level, then therapeutic impulses will not result in any physiological change. So as we've said, we've got this central nervous system that has to prioritize afferent information. So all of this nociceptive, mechanoreceptive, proprioceptive input that's bombarding the central nervous system comes across as some sort of noise coming into the central nervous system. So we've got toxic sensory inputs coming in, and then obviously the central nervous system needs to make decisions about that. So this happens at the dorsal horn and there's higher centers where this neural gate system is functioning. So the central nervous system has to make decisions about this noise and prioritizes whether it needs to be perceived or responded to. And then we have afferent priorities. So as a result of this abnormal input, then there's going to be abnormal output. So there's going to be disturbance. So the afferent input, the highest priority, will lead to efferent changes to respond to the threat. And this will always be manifested in some kind of functional motor changes. So this is not just necessarily muscle tightness. Any kind of physiological function has potential for motor changes, output changes. So these will be the clinical changes that we use and observe to guide decisions about what to do. So again, referring back to previous workshops, so we've talked about the 6 whys of physiology, of health, of subluxation. So we have adaptability, we have flexibility, we have pliability, we have renitency, we have tensegrity, and we have piezoelectricity, so the 6 whys. So this is a linked, coordinated system. So at the center is adaptability. This is the requirement. In order for a physiological system to survive and thrive, it needs to be adaptable. And all of these other processes going on around it that are interconnected and interwoven, they're all coordinated together to create normal physiology, healthy physiology. So the adaptability is the capability of a system to maintain homeostasis. So we talk about homeostasis. We have to have level, static findings inside the internal physiology. But the only way this can be achieved is via the continuous ability to adapt to changes in internal and external environments. So there is no stability without continuous change. And that's what adaptability is. It sits at the center of all the physiology. Everything is designed to create an adaptable system. So then we have flexibility. With any system, there is a range of motion. There's extremes of how much and how little is achievable. And the system has to have a range of motion. The bigger the range of motion, the greater the ability to survive, the greater the ability to adapt. Um, so a system has to be flexible, has to be able to go from high to low and anywhere in between. Then we have pliability. So pliability is different to flexibility, similar but different. So the system has to be elastic, has to be able to stretch while it's under the load of the internal and the external environments. So without pliability, there can be no flexibility. Without flexibility, there can be no adaptability. And then we have this concept of renitency, which D.D. Palmer spoke about in some of his early texts. So this is talking about the strength of the tissues to withstand these stresses and strains of life over time without failing. So they're not going to break down, they're not going to degenerate, they're not going to snap, they're not going to tear. They're able to keep going over years and years and years of stress and strain. So a system can be adaptable, flexible, and pliable, but if it's not renitent, then it's going to break. Then we have the idea of tensegrity. So again, we've talked about this in the past in terms of architectural principles, engineering principles, and then biological principles, that so many systems rely on this design principle. So the balance in biomechanical design between stability and flexibility has to have shape, has to have strength, has to be flexible, and it's all built into the design. So it withstands the strains of compression and movement, maintains its ideal shape, and possesses coordinated capabilities for movement and function. So it's all interconnected and interrelated. So again, tensegrity, different, similar, related, interconnected. Then we have piezoelectricity. So everything has to work based on electrical and energetic principle. So the biofeedback all depends on piezoelectricity, which monitors, controls, and coordinates all functions. So we need piezoelectricity to create all of the communication and all of the energy required to do all of these other things. So we're going to be talking about a test we're going to use to test all of these things, to test adaptability, to find the dominant neurological layer. So the anatomical leg length discrepancy is what we're going to be using. So we're relying on a basic normal anatomical variant, and that is leg length. So according to research, the average leg length discrepancy is around 5 millimeters. Now, I know that there have been estimates of more and less, but this is the one that we're using from the strongest evidence base. So obviously some people are going to have a larger difference, some people are going to have a smaller difference in this, but it's very rare to find people with perfectly even leg lengths. So this creates an unusual challenge to the weight-bearing physiology, and we'll explain this in a moment. So we have a person, let's say they have a 5 millimeter leg length discrepancy and they're standing on 2 feet. So if nothing happened to adapt for that anatomical difference, when we stand, one sole of one shoe will be 5 millimeters away from the floor. Or we would lean to one side to fall to the side of the short leg, like a leaning Tower of Pisa, and we would all lean just to one side to get both feet flat on the floor. But we know this intuitively, this is just common sense in a way, that adaptability will allow neuromusculoskeletal system to create changes which results in both soles of both shoes being flat on the ground when we stand up against gravity. And so The 6 Ys of physiology are necessary, are essential for neuromusculoskeletal system to compensate for one simple anatomical variant. One side's shorter than the other. So without adaptability, we would indeed spend our lives with one foot missing the ground. Maybe we'd trip over the long leg, maybe we'd wear the long leg shoe out very quickly. Maybe this would explain why we're lost in a desert. We walk around in circles, who knows? So we need flexibility. There has to be a range of motion. There has to be an ability for the system to move that 5 millimeters at least. That flexibility has to be at least 5 millimeters to allow the shorter leg to reach the ground at the same time as the long leg. In order to do this, it has to be pliable, has to be elastic. So the soft tissues would not be capable of stretching in all the places needing to stretch to achieve the 2 feet flat on the floor. And then renitency. What would happen over time with all of these uneven stresses and strains? Without renitency, tissues would eventually break down due to sustained uneven forces and strains created by asymmetry and by unilateral loading. But we walk for years, decades. Tensegrity. Without tensegrity, all the necessary adaptations would not be connected and coupled. So as one area moves to compensate, another area has to move. That's all coupled and connected to those changes. When one thing moves, everything else needs to be connected with its own required movements and its own required changes. And then obviously piezoelectricity. There has to be communication. Without piezoelectricity, the head wouldn't know what the tail was doing. So this neurobiofeedback that's always happening inside our central nervous system is essential to connect all of the adaptations required throughout the entire system. So we get to our adaptability testing. So the test we're going to use to assess adaptability relies on 2 different neuromusculoskeletal states. First, non-weight bearing. So in the case of most musculoskeletal therapists and chiropractors, this is in the prone position. So in the prone position, the neuromusculoskeletal system is in more relaxed state. So if you think of a car sitting in the garage, the engine's running, but it's not going anywhere. It's just ticking over at a resting RPM. So similarly, that's our central nervous system when you're lying prone. It's just sitting there idling. So in this position, if we look, we'll see that the feet will be more plantar flexed, and likely they'll be more supinated, and the foot arches will be more curved. And if we passively observe, it may look like one leg appears shorter than the other, but at this stage, we're not sure whether that's anatomical difference or functional difference. Then we move to the weight-bearing position. So now we're a car. Instead of just sitting in the garage, now it's reversing out of the garage. So it's under greater strain, greater demand. So when we move from the non-weight bearing to the weight bearing, changes are required to achieve 2 soles of feet flat on the floor. So first thing, feet and the ankles have to dorsiflex. We're not going to walk around on the balls of our feet or our toes. Feet and our ankles will have to pronate, so we're not going to be walking on the outsides of our feet. The arches will partially collapse and stretch to start to create shock absorption. And obviously, they're also going to have to be these compensatory adaptations occur in the rest of the musculoskeletal system. Maybe only up to the pelvis, maybe all the way up to the occiput, and in an attempt to compensate for this 5 millimeter difference. And it may fail or it may succeed in this quest, depending upon the adaptability. So obviously, all of the necessary afferent and efferent neurological pathways have to be activated and coordinated to achieve upright balanced posture. So here's some claims that we're making and assuming in this process. So in a system that has high adaptability, The ability to achieve 2 feet flat on the floor will be almost instantaneous. Whereas in a system lacking adaptability, it will be a slower and more resistant, a stiffer process to achieve 2 feet flat on the floor. So if we utilize a process comparing observable non-weight bearing to weight bearing leg lengths, we can assess the degree of adaptability being displayed. So this yardstick can be used then to identify the dominant neurological layer, which when stimulated in a way that improves adaptability, so reduces neural gate dysfunction, will help identify location with maximal permission to deliver therapy. So we're going to be using what I call the weight-bearing adaptability test. So what we're doing is we're attempting to mimic the weight-bearing response with our procedure. So we're going to imitate being the ground. We're the gravity with our testing procedure. So in terms of identifying the dominant neurological layer, another question that can be asked of the human physiology, which therapeutic impulse do you like the most? So once we've determined the level of adaptability, we can then apply a stimulus into the skin to create afferent pathways, which will result in efferent changes. And if we touch the dominant neurological layer, we're going to see increased adaptability. So we'll be talking more about this in the next workshop. So again, go to the website. You can find a lot of these workshops. The next workshop will only be available in the program section because it will be discussing the clinical, technical, and practical application of how to apply an adaptability test, how to find a dominant neurological layer, etc.